procedures. This is our proprietary material. In this video, I'm going to explain more about blocking and non-blocking assignments and different kinds of statements like if, else, for loop, execution branching statements, and task and functions. Blocking and non-blocking. Now let's recollect what we discussed about procedural block. So within procedural block, basically we can use both blocking and non-blocking. But I want you to remember the concept of procedural block. There are two kinds of procedures. One is initial, the other one is always. Initial happens only once, and always the execution happens continuously. So when it comes to always, you have to define sensitivity list. You can have more than one initial block, you can have more than one always block. That's how usually we write test bench or RTL. Now let's look at the syntax of procedural block. The block can be either initial or always, and you have to define sensitivity list in case of always block. And while defining sensitivity list, basically you have to include all the signals. And if you are not sure, you can also think of using star, that's implicit. And the block can have name. Later on, through hierarchical scope, you would be able to refer any variable which are local to the procedural block. And you can have local variable declaration within procedural block. And using procedural assignments, basically you define the functionality. This is where you would be using either blocking or non-blocking. That's what we are going to discuss now. And the block can have begin end, right? So if it's going to have multiple statements, you have to group the statements using begin end. This is how the syntax looks like. Type of block, for example, always at sensitivity list, begin, name of the block, define local variable, define the statements, end. Now let's look at blocking. Blocking assignments happen one by one. The execution of one statement blocks the execution of next statement, something like this. Here, always at passage clock, Q1 equal to D happens first, then Q2 gets value of Q1. So now Q1 is D, right? So Q2 is D. Then Q3 is Q2. So Q3 becomes D. It happens one by one. So the current value of Q3 is D. Order is important. Here, look at this example. A is 0, B is 1, and A equal to B. Now, the value of B is 1, so A is 1. And B equal to A, so B will also be 1. And if you display, both will be 1. All right. With delays. When it comes to blocking assignment, whether it is right hand side or left hand side, everything is going to be cumulative. It's straightforward. Always visualize like this. You don't really need to analyze whether it's intra-assignment or regular delay. You remember the right hand side is intra-assignment delay and the left hand side is regular delay. Okay, so here A equal to 1, B equal to 0, C equal to 1, and D equal to 0. There are values and how the assignment happens. Look at this. The initial value is A is 1, B is 0, C is 1, D is 0. And after 5 nanoseconds, C gets the value of B, which is 0. So C becomes 0 after 5 nanoseconds. Look at here. Whether it is right hand side or left hand side, just add the delay. Then after 15 nanoseconds, this is 5, this is 10. Okay. So after 15 nanoseconds, D becomes A. So A is 1 and initial value of D is 0. So 0 to 1 happens at 15. Where is D? The 0 to 1 happens at 15. And after 15, D gets the value of D. D initial value is 0. Now D value is 1. So B also becomes 1 after 15 nanoseconds. So after 15 nanoseconds, D becomes 1. Look at this example. A is 1, B is 0, C is 1, D is 0. Okay, so you can find the initial value. And C gets the value of B after 5 nanoseconds. But here there is another delay. So C is going to get the final value after 10 nanoseconds. So what is the value of B? 0. And C is going to change from 1 to 0 at 10 nanoseconds. Here, 1 to 0 happens at 10 nanoseconds. And 10 plus 5, 15. After 15 nanosecond, D is going to get the value of A. A is 1 and D's initial value is 0. So 0 to 1 happens at 15 nanosecond. Where is D? 15 nanosecond, D is going to change from 0 to 1. Then 5 plus 5, another 5, then 20. At 20 only, the value of B is going to change. So the B changes at 20. Analyze it. So in case of blocking, it's simple. You have to add all the delays. That's it. But in case of non-blocking, it's going to be different. Non-blocking. This is the symbol. This is how we define non-blocking within procedural block. This is not less than or equal to. Okay. If we are going to use this symbol within if else, then this will be treated as less than or equal to. But if you do normal assignment, this is going to be treated as non-blocking. So non-blocking, how you do? The execution happens in parallel. So here Q1 gets D, the previous value of Q1 goes to Q2, the previous value of Q2 goes to Q3. Everything happens at the same time. So the execution wise, if you look at, basically it takes the right hand side value, assigns them to a temporary variable, and then it schedules the final assignment at the end of simulation. That's how non-blocking assignment happens. Within initial block, if you do like this, if you mix blocking and non-blocking, usually we don't mix. So here what happens, A gets the value, B gets the value, 0, and B gets the value after 10 nanosecond, value of A, and C gets the value of B at 0, because these two will happen at the same time. So resulted values are stored in temporary variables and assigned to all the outputs simultaneously at the end of execution block. So in this case, B is scheduled to get A after 10 time units. So here C will get 0 at 0 nanoseconds. Okay, we will look at some more examples. Non-blocking assignment. The order of execution of distinct non-blocking assignments to a given variable shall be preserved. So look at this example. I equal to 1 tick D0, I equal to #5, 1 tick D1, but both will happen in parallel. So here schedules I equal to 0 at time 5. So whether I is going to be 0 or I is going to be 1, obviously I is going to be 1 at time 5. This overrides previous assignment. That's how the simulation is going to happen. Here, look at the synthesis aspect. Blocking, input D, clock, output Q2. This is reg Q1, and at passage clock, Q1 equal to D and Q2 equal to Q1. So Q1 gets the value of D. Now the current value of Q1 is D. So Q2 gets the value of D. So basically these two statements will be simplified as Q2 equal to D. So there will be one flip-flop. Okay, the D will be assigned to Q2 at the edge of clock. So there is only one flip-flop. And if I use non-blocking, both will happen at the same time. So D is assigned to Q1. At the same time, the previous value of Q1 is assigned to Q2. So it's like shift register. The data input goes to Q1 and the previous value of Q1 goes to Q2. Look at here. Data goes to Q1 and the previous value of Q1 goes to Q2. It's kind of shift register. Two flip-flops will be inferred. So if you use blocking, it will infer one flip-flop. If you use non-blocking, it will infer two flip-flops. Let's look at some more examples. So if you write code like this, there are inputs x1, x2, x3, clock. Output, we define outputs f, g as reg because we are planning to use always block. The left hand side must be reg data type. So you have to define output like this. Always at passage clock, f equal to x1 and x2, g equal to f or x3. So in this case, it will infer hardware like this. At the edge of clock, f is going to get x1 and x2. x1 and x2, the value will be assigned to f. So you need flip-flop because everything happens at clock. When you say clock, the value will be assigned at clock edge. So for f, it will infer flip-flop. And for g, there is another flip-flop. What is the value of g? F or x3. So this value will be odd with the x3. There is another OR gate, and this is how it assigns value. Got it? One more example. If you use non-blocking, how it happens, x1 and x2 and f or x3, there is a difference. So it performs x1 and x2 and assigns the value to f. The previous value of f will be ORed with x3 because it has to happen in parallel. When it does this calculation, at the same time it assigns the previous value of f. It takes the previous value of f and performs the operation, and finally it calculates. So the value of g depends on the previous value of f. Look at it here. The previous one, if you go back, it's different. This is blocking. So it's going to happen one by one, right? So the circuit will be like this. Here, it takes the previous value of f because both will happen in parallel. This is non-blocking. So there are some coding guidelines. It's best to use blocking assignments for combinational and non-blocking for sequential. That's how we do. And this is multiplexer, so we use blocking. And for sequential, we use non-blocking. Do not mix blocking and non-blocking in the same always block. When combining combinational and sequential code into a single always block, code it as a single block. Okay, you don't really need to do something like this as a separate block. Look at here, you calculate the value separately for y, that is combinational, and then you pass that variable and assign the value at clock edge. Instead, you can write it in simple way. This is also equivalent. Always at passage clock, reset the value and then you perform the operation and assign the value directly. You don't really need to make it as two always block. When combining combinational and sequential code into a single always block, code the always block as a sequential always block with non-blocking assignment. That will do. Okay. Now you want to make some decision, you can use if else, something like this. If the result is going to be true, then it executes something. If it is going to be false, then it does something else. So within procedural block, you can have if else. And within if you want to have multiple assignments, you need to use begin end. So the rule of begin end is whenever you define more than one statement, you have to use begin end. If it is going to be a single statement, no begin end. You can also have if, else if, else if, else if. The first one will have highest priority. This is another form. One is if, else. The other form is if, else if, else if, else if, else. You can have n number of levels. And case expression, and if the result is going to match with any particular branch, then that particular statement will be executed and there will be a default statement. Here, look at this, always sensitivity list, case, we are looking at the variable x. If x is going to be 0, then z gets the value of a. If x is going to be 1, z gets the value of b. Else, if x is going to be something else like unknown, z gets the value of c. So it's good to cover all possible values through default. That will avoid unwanted latches. We will discuss about it during synthesis. You can also cover multiple conditions like this. If x is going to be either 0 or 2, it takes this. If x is going to be either 1 or 3, it takes this. Or default, z is going to be c. Case with don't care. Case A, if it is 0, then z gets the value. If it is 1, 0, 1, z gets the value of 0, 1, 0, or default. Okay, now look at this. A equal to, let's say the value becomes 1, 0, x. It does not match any case item. So the default will happen. You got it, right? So A gets the value 1, 0, x. It's neither 0 nor 1, 0, 1. It's going to be 1, 0, x. And that is not matching with any of these values, so default will happen. But if you say case x, the x will be mapped with either 1 or 0. So 1, 0, 1 will be considered in this case. 1, 0, x matches the second case because x can be either 1 or 0. So when you say x, basically it's also going to consider the x. And the x can be either 1 or 0, so it's going to consider this branch 1, 0, 1, and z is going to get the value of 0, 1, 0. And looping statements, you can have for loop. So for loop looks like this. This is initial value, this is the conditional statement, this is the incremental. Three things you have to define, and the execution happens based on these values. It's going to start from 0, and it's going to increment by 1, 0, 1, 2, 3, and then once it reaches 10, then it will stop. So I should be less than 10. So it's going to execute from 0 to 9. That's how it works. And while loop executes statement until the expression becomes false. This while loop executes the loop until this expression becomes false. This is non-synthesizable, meant for test bench. Repeat and forever loops. We can repeat a particular loop for particular time. Repeat 5 at passage clock. So here you are not using begin end, so it's going to consider only one statement. So there will be 5 passage clock. It's going to repeat. So the simulation will advance by 5 clock edges. Repeat. But when you say forever, it's going to happen continuously, right? So the clock is going to toggle for every 5 nanosecond continuously until you stop the simulation, right? So that is called forever execution. We use forever mainly to generate clock, something like this. So here, the initial value of clock is x. So you initialize this, it becomes 0. Then it's going to toggle 0 to 1, 1 to 0, 0 to 1, 1 to 0, something like that for every 5 nanosecond. That's how we generate clock using forever loop. We discussed about blocking, non-blocking, if else, for loop, forever, repeat, while. Now let's look at tasks and functions. Functions can enable other functions but not tasks. Okay, functions and tasks, they are like subroutines. You can define a particular functionality using either function or task, and then you can call this functionality anywhere n number of times. So it's something like subroutine. There are two ways in Verilog. One is through function, the other one is through task. And function, mostly we use this for RTL. You cannot have any delay within function. It cannot accept delay. And function can call another function but not the task, because the task may have delay. So task is meant for test bench, and you can even use it for RTL, but function can be used only for RTL. When it comes to test bench, you have to really think of avoiding delays, because function cannot accept delays. And function can have more than one input argument. It always returns value through the name of the function. So the return value must be a single value. It cannot have output argument. So the syntax would look like this: function, name of the function. You are going to get the value through the name of the function. So you need to define the name accordingly, and there is input. You define the functionality. So here, this function calculates the parity. Input is data, and parity calculation happens through this operation. It performs the calculation, and the value will be assigned to parity underscore cal. So basically, you are going to get the output through parity underscore cal. This itself is a variable. And when it comes to assigning the value, so this is how you call the function. You pass the address goes here, it calculates the parity, and then the value will be assigned to another register. Task. Task can enable other tasks and functions. Task can have delay. Task can have inputs and outputs, even in-outs. Look at this. Task, name of the task, input, in-out, output, and begin end. The same example you look at, task, parity calc, it has both input and output, and it calculates the parity. Now this is where you are calling. So basically, when it comes to task and function, you have to define them, and then you need to call them separately. It's like subroutine. So here the task is defined. This is where you are calling. Every time when the address changes, you are calling the task, and you are passing both input and output. The address is input, parity underscore reg is output. So address goes inside. So here address will be used to calculate the parity, and the value will be assigned. All right. So in this video, we discussed about blocking and non-blocking. Remember, blocking happens one by one. And when it comes to delay, you don't really need to think too much. You can add all the delays in case of blocking. It's going to be simple. And non-blocking, the execution happens in parallel. And there are different kinds of loops, forever, repeat. Forever, the execution happens continuously, repeat for a specific time. And you have two ways how you can define subroutine, task and function. And function cannot have delay, task can have delay. And function returns the output through name of the function, and task has all the arguments, input, output, in, out. So you always produce output through output argument. Thanks for watching this video.